What you need to do for homework? When I said specular, I didn't mean just add the specular highlight. In fact, I didn't even insist on the specular highlight. What I wanted was those recursive reflections. Okay, question?
Are we emailing it to you?
Yeah, just email me the homework. You don't have to worry about that hand-in stuff. Just email it. I'm sorry I even copied that onto I started from a template of another course I taught, and I should have just not even mentioned that hand-in stuff. Just email me the files you the files you changed out of the source, not the rest of it, and at least one image. It's really the image I'm going to look at. So today I want to talk about the Cook-Torrance BRDF, and it makes an attempt to be more physical than the Phong or Blinn highlights. And the idea, as I think I mentioned maybe last time, is it's modeling the surface as a rough surface with a bunch of facets. So the average surface normal is in, but a facet normal that catches the light from input direction, say psi, and reflects it exactly into viewing direction, say theta, to make these two angles equal. We're assuming that any light that comes from this direction that gets reflected in that direction is reflected off of a small flat facet with the normal exactly bisecting this angle in order to make that facet reflect all the light in this direction into that direction. So as I said, H, this halfway vector, is the sum of these two vectors. You can think of them as vectors divided by the absolute value of the sum. And so what we need to know, among other things, is what's the reflectivity, because no mirror is perfect, and how much of the light that could come in is sort of hidden by another bump on the way in, or maybe light came in here but was shadowed by another bump on the way out, occluded. So it didn't, all the light on the facet doesn't get out. And then we want to know how many facets there are in the correct direction. So the formula for this, it should be lowercase fr, and in the notation in the book it's at a point x and taking light from this direction into that direction, but there are two arrows instead of just one because it satisfies reciprocity. It would be the same in both directions. And this is some function of the angle beta. Beta is this angle here. It's the angle between theta, the outgoing direction, and this facet normal, and it's also the direction between the facet normal and incoming direction, because the facet normal is oriented to bisect that angle. And this is the Fresnel factor, which we'll talk about later when we talk about refraction. It has to do with the physics of the electromagnetic waves and how they are either reflected or transmitted or absorbed near the surface of a particular material. And you probably already skipped over the formula in the book for that. And then there's a pi in the denominator. We'll see later it was just stuck in so that this was similar to the diffuse reflectivity BRDF, which had the fraction reflected divided by pi. But in fact, that pi is inappropriate in this formula, as I'll point out. But Cook stuck it in to make it look that way, look like the other one. And so then we have a facet distribution function, h, which I'll spend most of the period talking about, which has to do with the density of the facets oriented in a particular facet normal direction h. How many of them are there, and what are their area to actually catch that reflection? And then there's a geometric factor. And that geometric factor has to do with maybe some of the light that could have hit this facet is shadowed or could have reflected from this facet toward the viewer is occluded by this corner. And it turns out that number depends on the surface normal and the directions psi and theta. And of course, n is a function of these two, so n could be in the formula too. I mean, h could be in the formula too, but these are the three variables that it depends on. And then we have some stuff in the denominator, n dot psi and n dot theta. And what I want to emphasize at this point is this satisfies reciprocity also, because the how can I say it? H will be the same if you switch phi and psi. I'll show later when I write the formula for this factor, this is going to be the same when you switch phi or psi. Basically, occlusion is just switched with shadowing, but the amount of that facet which is actually visible to both the light source and the viewer is really what we care about. And so that certainly doesn't depend on how we switch them. And then here, they both appear here. Okay, so what do we really mean then by this facet normal distribution function? I'm going to start with a number count distribution. And then later I'm going to put Cook's version of this and how it relates to that one. And so my number of count of facets here says how many facets of area, say, FA. So for now, I'm going to assume all these little microfacets have the same area. And that we really then are just counting how many of them have normals in direction H. Okay, but if we just say it that way, we have the same problem as talking about how much energy off of a rough surface reflects exactly in a given direction. Because to get all the microfacets, we have to actually integrate over the hemisphere of possible, microfacets that are at least not tilted overhanging. So it's really a distribution function. So as a distribution function, it's going to be how many facets per unit solid angle or per near H. So what that means is it's a distribution function. And so if we really want a number, maybe I'll put it on the board here, the number of facets in a solid angle say d omega h near H is okay. Well, we can't just talk about the number of facets on the whole surface area. This is how many facets how many facets in a surface area dA. Right? So we have, here's the surface, and here is some area on the surface, say dA, near X. And we want to count the number of facets with this normal in a certain solid angle near H on that surface, because this distribution function is really per unit solid angle per surface area. So that means what we have to do to get actual number of facets is to take that density and multiply it by the solid angle W d omega h, and multiply it by the area dA of the piece of the surface we're talking about. And that means the total area, maybe I didn't write all the words here because I should have said per surface area, and this is per solid angle. And so we multiply it by the solid angle of the surface area and we get the count, and then the total area of these facets, we have to multiply that by this FA times this number. So we have that much area. I may make it a handwriting S there and connect it. That's not the, it's these. And we want to know how much light is reflected. We want to know the radiance reflected in the direction theta. Well, again, if we go back to this picture, what we really have to worry about is light is not coming in from this specific direction, unless you have an infinitely bright point light source. The light is actually coming in over a solid angle d omega in, which the book would write d omega for this incoming direction psi, and it's going out in a solid angle d omega out, which is the same as d omega for this outgoing direction. So we really have three little cones of solid angle here. The h can vary. It's got its own d omega h that we have to put in to count for the fact that this facet density is also a distribution function of solid angle that you have to integrate d omega to actually get a finite number out of. Because we're going to assume the facets are randomly oriented. It's not like all the facets are in a single direction, in which case that would be a delta function. But it's a sort of a random rough surface. So I guess what I want to do is compute the flux that hits this facet from this solid angle. And then I want to see how much, one way to think of it is, if I have a solid angle of incoming directions and a solid angle of normal directions, and both of those wiggle, that's actually going to determine the solid angle that the light comes out in. Okay, so suppose we have incoming flux L in d omega in times dA perpendicular. That's sort of a flux in. And this dA perpendicular is measured perpendicular to this incoming beam. And now what we want to find is how much of that flux hits this surface. So we need this angle beta between the incoming beam and the normal to that surface. It's not the normal n to the flat average surface. It's the normal n to this surface. And that means this dA perpendicular is, let's see, it's going to be cosine of beta, isn't it? Actually, cosine of beta is the same as psi dot h. Right? That's cosine of the angle between the incoming direction and the normal to this little facet. And if we multiply that by the area of the facet, then we get the area perpendicular. So I guess if we multiply it by the total here, count of the facets with this area, we'll have d of h, d omega h, and then dA here. Right? Because this was what I had before was only one facet. This is the amount of light flowing in that incoming direction that per unit surface area of the how can I say it? Times the surface area of all the facets then within that original dA worth of surface that are reflecting in this direction. I mean that have normals in that within this bin. So that's how much flux they intercept. And now some fraction of that flux, which is determined by this Fresnel law and this shadowing and occlusion fraction, get out. So I'm going to leave them out of that formula. I'm just going to assume 100% of that flux actually is coming out. Okay, so what I'm interested in is L out. Let's see, maybe I'm always worried that the camera is going to be going back and forth between boards. I guess it's going to have to, or maybe people are taking notes or running the the webcast backwards and forwards, just jump from board to board. I'm going to write L out. L out is supposed to be the flux coming in or the flux coming out. The flux coming in is, we're assuming the flux coming in is the same as the flux coming out. So why don't I write it just, why don't I just write it as flux? Actually, I called it d phi there. Divided by the area perpendicular to the beam going out, and so that's dA was the area of that surface patch in question, times the angle n dot theta. This is the cosine of the angle on the way out, right? Because it's got to be measured per unit area perpendicular to the outgoing beam. And this is the area on the surface, and now this projects it perpendicular to the outcoming beam times d omega out. So that's the radiance out that we're interested in. You know, after you put in the geometric occlusion and shadowing factor G and the Fresnel factor F. So I guess I can copy d phi in from the other board, since I said I'm going to neglect those factors for now and assume 100% was reflected. And so that means I have L in, I'm just copying from this other board. Wait a minute. I forgot my L in d omega in from this formula, didn't I? I had the dA perpendicular of the facets, which was this much, and I still need my L in d omega in. So I have L in d omega in times the facet density, what else do I have, times the solid angle of the facets, times the area of each facet, times dA, times L in d omega in. And in the denominator, I also have a dA, and I have an n dot theta, and I have a d omega out. So I guess all I can And I missed this psi dot h factor too. Sorry. Yeah, I do. I forgot them once, and now I overdid myself in compensating by putting them in here, and then copied them from here again. Thank you. So now I have psi dot h. So I'm just going to cancel out the dAs and reorganize these terms a little bit. I'm going to put D, I'm going to have a fraction that I'm going to compute next. D omega h over D omega out. And then what I have left is in the numerator FA D of h psi dot h. And I'm canceling the dAs. And over here I have n dot theta and a d. Well, I wrote my d omega out as part of this fraction, and the dAs cancel. So I guess that's what I have. So what is this? I mean by this? What I'm thinking of initially is light is coming in from a single angle theta. Forget about the cone for this argument. We're going to assume light comes in a single angle theta. I'm sorry, the incoming angle was psi. Single incoming direction coming from this single incoming direction psi. And I have these facets, and I'm thinking of the facet as like a little mirror, and I'm wiggling it a little bit. So the facet normal is wiggling. And make it look like it really looks normal. It's a little bit tilted. In fact, let me make this angle a little steeper so it doesn't get away in my cone. Here is my d omega h. And here's my incoming psi. Here is, say, the h at the center of the cone. And what I want to know is if I wiggle this cone, if I use this cone to change the angle of this microfacet a little bit, how large a cone do I get for this outgoing direction? Here is the outgoing direction theta, and I have a resulting cone around here, d omega for theta, which I've been calling d omega out. How big is that? Obviously, if I make this thing bigger, that thing is going to get bigger. But what's the ratio? So we can actually compute the ratio with trigonometry. What I'm going to do, maybe because I want enough space for it, I'm going to go back to, let's see, what do I need to keep? I guess I don't need to keep any of this. I'm going to make a sphere, and I'm going to make the north pole of the sphere actually point toward the incoming direction. So this is the incoming direction psi. And then somewhere on this sphere, maybe shall I draw the equator? Maybe I don't need the equator. Is direction h. And I have a longitude line for h, and I guess I have a latitude circle for h. Right? So this angle from, what do I call this? I guess I can use theta and phi for the spherical coordinates. So this is theta for h. And if I project it down on the equator here, and say this is my x-axis on the equator, I have the projection of this, I guess this arc here is intersecting the equator, and I have some angle here, which is the phi for h, on the equator, and those are my two spherical coordinates for h. And knowing h and knowing this psi, I know that whatever this angle is, I have another angle that's twice as far that gets me down to the reflected direction theta. Basically, whatever. So here, my h I can think of in coordinates theta h, phi h, where this is the angle to the North Pole and this is the angle around the equator. Then this reflected direction, the theta is going to be twice as much, right? This angle equals that angle because this normal has to be halfway between the two of them. And so this, what did I say? This is 2 theta h, and the phi is the same, right? Because this is the plane through the normal and the incident direction, and the reflected direction is in that plane. Right? Because the plane, it's reflecting off of a plane which is perpendicular to h. So this angle equals that angle in the same plane, so the phi h is the same. Okay, but what we're really interested in is how solid angle changes from here to here. Right? So suppose we have this, here is d theta h, and over here is a d phi of h. Right? Then the solid angle d omega for h is, what is it going to be? The formula said it was, because this radius along here of this, circle that isn't a great circle, it's some sort of small circle here, has radius, let's see, this was theta here, so this is sine theta. So the solid angle is sine theta d theta d phi. I guess these are all h's. Well, I don't know. We'll keep them h's, I guess. What we really need to know is, what's this? Well, because this angle is double this angle, that means if we increase this angle by a certain amount, the increase here will be twice as much, right, to keep this one be double that. So this one is d theta, d theta for, I guess, capital theta. Lowercase theta measures this angle, capital H theta is the outgoing reflected direction. That's 2 d theta h, because this angle was double that one. But this one, what we need to know is, what's the radius here in the same plane, right? Perpendicular, measured here. So that means that this thing is sine 2 theta h, right? Because this angle here was twice this angle. So this radius is now sine of twice that angle. And so that means that this d phi here, right, I've totally messed up my picture. Let me put my reflected direction here somewhere. And what I'm interested in is, what is this length of this arc? This length is this sine 2 theta h times d phi. The phis were the same. Right? I could put h on all of them. So d omega for theta, or for the out direction, is, do you remember how you find sine of twice an angle? Sine 2 theta, do you remember anybody the trig formula for that? It's twice sine theta times cosine theta. Does that sound familiar? So this is twice sine theta h cosine theta h. And then we have to multiply. That's the part going around this way, and the part going around that way, times d phi h, and then multiplied times 2 d theta h. Okay, so what I want is this ratio, d omega, this one over that one. So that's this ratio over this thing, and the d thetas cancel, the d phis cancel, one of these signs cancel, and I'm going to end up with this d omega h d omega out. I should have just called it out instead of capital theta there, and I wouldn't have had two thetas in the same formula with different meanings. Let me just see if my notes agree with that. 1 over 4 cosine of theta, which is, since theta was the angle between the incoming direction and this normal, remember on the other board this was the North Pole, and this was the h that I was talking about wiggling, this cosine theta is going to be n dot psi. So that means for this formula here, I can, instead of rewriting all these terms, why don't I just replace that by 1 over 4 n dot psi. Okay, so now can I erase this to continue from here? So what is the BRDF? FR is, wait a minute, I already have FR, right? I said L out. No. This is L out is flux per unit area normal to the beam. FR is L out over E in. Right? Because the definition of a BRDF is what you have to multiply by the irradiance to get the radiance out. So I have still, in order to find the FR, I still have to divide it by E in. So that means I have, let me copy from the other board, L in d omega in times F A dH psi dot h. And then over here I have, in the denominator I have, oh, I see, I can cancel this, right? This one is here, to go back a board, and this one is here, so I don't need that psi dot h after all, because it cancels with 1 in the denominator. And then I have 4n dot theta. And now I have to divide by E in, which is L in d omega in. Right, that's the flux in per unit area normal to the beam. And then to get per unit area on this surface, I have to multiply it by the cosine of the angle between the beam and the surface. And so that angle is n dot psi, right? The surface in question is now not the microfacet, it's the whole surface, because we're talking about how those microfacets contribute to the light coming off of the whole surface. Okay, so now these things cancel. So how does this compare to the other formula that I have way over in the beginning? Well, if I wanted to have the true FR from this formula, I'd still have to put that factor F in and the factor G in. And then I have this FA density of H over 4 n dot theta n dot psi. And all of these D's are all these number density. If you multiply the number density by the area of each, you sort of get an area density of microfacets interpreted per area of the surface. What's the area of the microfacets, not their count? But that is not the DH that Cook chose. His DH is equal to 4 over pi times that number. Let's see, is that right? Or is it pi over 4 times that number? It's pi over... It's pi. His DH over pi is supposed to be this FA dNH, the number density, divided by 4. So if pi were equal to 4, then it would be the area density. But since pi isn't 4, it's a little bit different by the ratio of pi to 4. So that was a sort of a fudge that Cook used just because he wanted a pi in the denominator to look like that formula we got for Lambert's law. But if he, you know, when I carefully read his thesis, I actually sent him an email and said, you know, what's going on here? And he said, well, I just chose it to turn out that way. So if you interpret it that way, then this whole analysis makes sense. So I have about, do I have any time left? Yeah, I have about 13 minutes left to say a little bit about this geometric factor, because we're going to talk about this factor, as I keep saying, later on in the quarter. So this geometric factor deals with occlusion and shadowing. And this whole theory is taken from a paper by Torrance and Sparrow, published in the 60s, where they sort of did this analysis based on the assumption that the distribution of facets is such that if you have a microfacet here, it's really a groove. It's part of a groove where you have two opposing facets. It's like this surface was sort of machined in random directions by some sort of a sandpaper or milling machine that cut these grooves with equal slope on both sides randomly into the surface. And so the surface has grooves of random orientations, random slopes and orientations. And so the problem, so we can imagine we're looking down in one of these grooves. What are the cases that can happen? Well, what I'm going to do is I'm going to draw a groove here. You know, I'm drawing the rest of the surface. I should draw some sort of random wiggles here. We only care about these corners of the groove. I just have the rest of the surface so we can picture here is the normal to the average surface and here is the normal to a groove, say. Okay, and say we're looking, or I was thinking the other direction. Let me consider this half of the groove. So assume that here is the lighting direction. So I'm going to sort of draw sort of like the sun or a light bulb irradiating in this direction. So this is the direction to the light source. We've been calling the light source psi. And suppose your eye, actually maybe I should have made the light source be a little bit lower here. Sorry about this picture. I'm going to imagine your eye can only see part of it, and so can the light. But the amount your eye can see is more than the amount the light can see. So your eye is up here, and the light is over here. Then the fraction that is actually getting light and reflecting it towards your eye, actually the light in the eye should be, I should have drawn the groove so its facet normal was halfway in between the light and the eye, so it's something like that, I guess, where these two angles are equal. So the direction H is halfway in between. If it's the eye that's higher, the thing that's really limiting the amount that's illuminated and also visible is the amount that's illuminated. And in that case, I'm not going to go through the trig for the derivation. Let me just, did I write on my notes which was the case? Which term was which? I thought I did, but here it is. No, one more page here. Okay, so if the eye is above, here's your eyeball, and it's above the light, then the formula for that fraction of the area that's visible to both is 2n dot h n dot psi over theta dot h. And if it's the other way around, where your lower one is the eye and the upper one is the light source, my facet's still, my eye still isn't low enough to look like it's making an equal angle with the facet. When I sketch this, okay, here's the facet, here is the eye making this angle, and a corresponding angle over here is headed out toward. So the eye is now lower, and the light source is now higher. It's going to be exactly the reverse formula, right? It's going to be 2n dot h, but now in the numerator is going to be n dot theta instead of n dot psi. And in the denominator we can still write, there's no 2, theta dot h, because theta dot h is the same as theta dot psi. Because, as psi dot h, because h is halfway in between. Doesn't matter how we write it. These two terms are the same. But this term and that term are different, and it's whichever is going to give you the least light, right? If this is eye is above, it's this term that's going to give you the least light. And if the eye is below, it's this term that's going to give you the least light. And if both eyes are higher, then both the eye and the light source are sort of within this wedge, so that where make me an eye here, say, and a light there, so that this whole thing is completely visible to the eye and also completely visible to the light source. Then the fraction that comes out is 1. And if you take the minimum of these three, that will be, right, if you talk about the fraction as measuring this length, and as these things rise up, this length gets longer. Eventually it'll get longer than this whole fraction, and this ratio will be bigger than 1. So it's the minimum of these that gives you the geometric factor. And the derivation of these formulas you can find in a 1977 SIGGRAPH paper. James Blinn, Models of Light Reflection for computer synthesized pictures, and this is the proceedings of the ACM SIGGRAPH conference in 1977. He's got a good derivation. I think the original Torrance and Sparrows paper in the 60s also has a derivation. So I just figure, I spend most of the period on derivation, and to do a lot more trigonometry probably isn't worth it. But I sort of give a plausibility argument for what those geometric terms mean and why you should take the minimum. So the last thing I want to do today is talk about some specific facet distribution functions, only a couple of them. One is the Gaussian, which is just e to the minus, I guess I called my angle away from the normal of the facet, why don't I call it theta h? So here is the normal, and here is the facet normal, and this is the angle between them. And if they're really oriented randomly, if you think of the horizontal being the norm, the flat plane, and the normal is straight up, then if you have a certain tilt with that, you're assuming that these grooves have been cut randomly so that if I rotate the whole picture around the psi direction, it's not going to change, right? If it did, then you'd have preferentially oriented grooves, like you have sometimes on machined things where all the grooves are in the same direction. Then it catches light in an anisotropic way, causes reflections that depend on like how you turn that piece of brushed metal with respect to the light source, even keeping its normal the same. But if we assume that's not true, then this distribution only depends on this angle. And so this is a Gaussian distribution. But you need a constant in front of it so that it integrates to 1. Actually, it's a little more complicated than that, because this facet distribution had the facet area within that, at that angle. But what has to integrate to 1 is the ratio of the projected facet area to the area of this dA that we were talking about of the smooth surface. So for normalization, requires that the integral of the facet area density, this is the true area, not times cosine theta h. So this density theta h times cosine theta h times solid angle for h, which is really an integral from 0 to 2 pi, 0 to pi halves for theta. This is d phi, and this d omega is going to be then sine theta d theta d phi. So cosine theta from here, density of theta. This is the normalization that has to come out to 1, because it's the ratio of the total projected area of all those facets, where this is the thing that gives the projected area on the actual surface compared to the facet projection. And so you have to choose the C to make this be true, which means some complicated integrals. And there was one other distribution that I'll write on the board really quick, where you don't have to worry about those complicated integrals, because it works out analytically, m squared cosine to the 4th theta e to the minus tangent theta over m squared. So theta and tangent theta are really close for small theta. And m is sort of the root mean square facet slope. Right? If m is small, then this is going to get big rapidly, and e to the minus that is going to decrease rapidly, and that's going to give you a very shiny sort of glossy reflection. And if m is large, that means the facets are tilted more on the average. The surface is going to look rough. A given increase in theta isn't going to make this term grow as fast. But the basic highlight shape is very similar, whether you use a Gaussian or this Beckman distribution. And I think the book had both of these as examples of D of H. So that's, except for the Fresnel law and the details of this geometry, that's how the Torrance-Sparrow thing works. Okay, I'm done.